little bit provocative, but we will now go on with rolling noise, or more precisely impact noise, with Jens NIELSEN from Chalmers. So Jens is well known as a research professor in railway dynamics, and he worked a lot on vehicle track interactions and in many European projects. And also he's also a member of the International Committee for the IWRN, and we have a few IWRN friends here, both in the audience and in the panel of speakers. So let me just say in between that this kind of workshop is an interim between two IWRNs, and I'm very honored that some of our IWRN committees are here there too. So Jens, the floor is yours.
Thank you very much for the introduction. Hello everyone, and welcome to my home office. I hope that you are able to hear me even if I don't have a headset. Thank you to UIC for inviting me to present this work, which has been a collaboration between the Swedish National Road and Transport Research Institute, DB Nets in Germany, ISVR in the UK, and Chalmers University in Sweden. Next slide, please. Next slide, please. This figure illustrates an overview of the different rails in a turnout. Unfortunately, I don't have a pointer, so I cannot show the different details, but the crossing panel allows for wheels to travel along the two intersecting routes, in the through route and in the diverging route. Next, please. Traffic in the direction from the switch to the crossing is called facing move, whereas the opposite direction is the trailing move. As you can see in the photo on the right side, in a fixed crossing, the rails split into a crossing nose and two wing rails with gaps in between. Impact loads generated in the crossings may lead to severe material damage, but today we will be focusing on the radiation of impact noise. Next, please. Within this study, we measured noise and rail acceleration generated by passenger trains passing through a fixed crossing. The test site is located on the Rhine-Alpine corridor in Germany. And for this study, pass-bys were only recorded for passenger trains traveling along the rails D2 and D4 in the trailing move, that is from the crossing towards the switch. Next, please. I will now show a video from the test. Listen to the noise generated in the crossing. Note that the rolling noise is significant, but perhaps you think that the noise from the repeated impacts is perceived as even more disturbing. So play the video, please. Next, please. Rail acceleration was recorded using an accelerometer on the wing rail. And as you can see in the figure, each impact is easily observed in the acceleration data. However, although clearly audible in the video that you just saw, as we will see in the coming slides, these impacts were found to be less evident in the sound pressure signal. To demonstrate this, let's have a look at a few spectrograms. Next, please. In the spectrogram, we have frequency on the horizontal axis and time on the vertical axis. So in the rail vibration data, the spectrogram is mainly characterized by horizontal bands occurring at each time there was an impact. It can be seen that these impacts lead to rail vibration in a wide frequency range with most of the energy up to 1000 Hertz. Next, please. This spectrogram is for the sound pressure that was measured at 7.5 meters from the track. Here it's still possible to see some traces of horizontal bands due to each impact. However, this spectrogram is more characterized by vertical bands. These bands are caused by the wheel rail roughness and correspond to the rolling noise generated at the crossing. In particular, it can be seen that frequencies in the interval 400 to 600 Hertz are significant. To understand this, rail roughness on the wing rail and the stock rail was measured in front of the crossing, And it was found that the roughness on the wing rail, which was D2 in the previous photo, exceeded the ISO 3095 spectrum for wavelengths shorter than 8 centimeters, whereas the roughness on the stock rail was below ISO 3095. Possibly this is because of the limited access of grinding machinery to this section of the rail. In fact, it was confirmed that the high roughness level on rail D2 is the reason for the observed peaks in the sound level spectra at 400 Hz and 630 Hz. Note that the spectrogram includes the summed contributions of rolling noise and impact noise, and unfortunately it was not possible to separate these sources. However, from analyzing the test data, it was concluded that the contribution of the impact noise to the sound pressure spectra was small in this crossing, and which perhaps is not in agreement with what we perceived from the video. Next, please. In the rest of this presentation, let's focus on the impact noise. Why is it generated and how can it be mitigated? To begin with, let's note that the vertical position of the wheel center relative to the rail center line varies as it travels over a fixed crossing. And this is called the wheel trajectory. Most significantly, it changes from a downwards motion to an upwards motion as the wheel makes the transition from the wing rail to the crossing nose, or vice versa in the opposite move. The reason for this is the wheel conicity in combination with the variation in rail geometry along the crossing panel and the influences of these variations on the variation in lateral contact position on wheel and rail. This kink in the trajectory can be described as a dip angle in the crossing. Note that wheels with different stages of profile wear result in different trajectories with different dip angles in the same crossing. The red line in the figure is the trajectory based on the measured rail geometry from the field test and an assumed S1002 wheel profile. The figure also shows the trajectory for an S1002 wheel profile passing through a parameterized crossing model where the inclinations of wing rail and crossing were altered to generate different dip angles between 6 and 24 millirads. Next, please. Now, to predict impact noise in crossings, we need an extensive simulation model. First of all, to calculate the time history of the vertical wheel rail contact force, we need a non-linear contact model and simulation in the time domain. This may lead to long simulation times, in particular if we also want to predict noise from the rails at frequencies up to 5,000 Hz. To simulate noise, we prefer to use a frequency domain model, for example, TWINS. However, TWINS is a linear model that is not sufficient for the contact loading. So this calls for a hybrid approach. Next, please. So the prediction method applied in this study includes two separate computer programs. One, a time domain simulation model for dynamic vehicle track interaction, and two, the software TWINS for the prediction of noise. The idea is to determine an equivalent roughness spectrum that in the linear model gives the same contact force spectrum as the one obtained with the nonlinear model that includes the rail discontinuity, the crossing. So thus, in the first step, the force spectrum is calculated from the time domain model. Frequency domain model 1 is used to determine the contact force per unit roughness. And here you can see in the denominator that it includes the sum of rail, wheel, and contact mobilities. The equivalent roughness is the ratio between the contact force spectrum from the time domain model and the contact force per unit roughness from frequency domain model 1. This equivalent roughness is then converted into 1/3 octave bands for the noise prediction using frequency domain model 2. Now it should be clarified that frequency domain model 1 and 2 are usually the same model, but it has been shown that they don't have to be exactly the same. Next, please. So let's start with a time domain model to predict wheel rail impact loads. The vertical dynamic interaction between the wheel and the crossing was simulated using so-called Green's functions. The vehicle track models are linear, but the wheel rail contact model is non-linear according to Kalker. The wheel model is either a rigid mass or a flexible model accounting for modes up to 4,000 Hertz. And the track model is developed using finite elements and consists of a discretely supported rail modeled by Rayleigh-Timoshenko beam elements with spatially varying beam properties. And the figures illustrate the ratio of maximum wheel rail contact load to static wheel load for traffic in the facing and trailing moves. And as expected, it can be seen that the impact loads increase with increasing dip angle and with increasing speed. Next slide, please. The next step is to use the calculated time history of the wheel rail contact load for the prediction of impact noise. To do this, the equivalent roughness spectrum was used as input to twins. In the noise simulations, a nominal rail was assumed and only a single wheel was considered. And the figure shows different characters of the impact and rolling noise spectra. All the impact noise spectra are characterized by a strong contribution below 500 Hertz, while the rolling noise spectra are dominated by several frequency bands above 500 Hertz. And for the rolling noise, with increasing speed, the contribution at the higher frequencies increases more than at the lower frequencies. Whereas for the impact noise, increasing speed results in an increase in noise spectra across the entire frequency range. Next slide, please. This figure shows the trend of overall A-weighted impact noise level versus speed, and it compares rolling noise with impact noise at different dip angles. The rolling noise is the gray curve that you can see in the middle of each figure. In the simulations, only a single wheel was considered, and results were rescaled to be representative to the fast averaging used in acoustic measurements. This corresponds roughly to traveling distance of 3 meters at the lowest speed and 8 meters at the highest. Again, as expected, the overall noise level increases with increasing vehicle speed and dip angle. And the speed dependence of the impact noise is approximately 30 log V, whereas the coefficient for the rolling noise is here slightly higher than 30. Now, if the impact noise levels had instead been evaluated over a time window corresponding to train motion of 20 meters, which was equal to the averaging length for the calculated rolling noise, then the overall level of impact noise would be 7 to 9 decibels lower than the rolling noise. And this is probably in agreement with the observations from our field test. However, sound spectra average over the entire length of the vehicle cannot capture and quantify the effect of impact noise completely. Next slide, please. So we have seen that the magnitude of the impact load and the level of impact noise are strongly influenced by the crossing dip angle. And because impact noise is also generated by the wheel rail relative displacement excitation, we can use similar mitigation measures as those that are effective to reduce rolling noise. For example, we can increase track decay rates. But it should be pointed out that stiffer rail pads lead to higher impact loads in crossings. Most important is to minimize the discrete irregularity at the crossing. However, a certain dip angle is required for the crossing geometry to be compatible with a range of wheel profiles in traffic. So there has to be a compromise in the design. Hollow one profiles induce significant impact loads in crossings. Thus, better maintenance of wheel profiles will also result in lower impact noise. Finally, a lower unsprung vehicle mass is also an efficient approach to reduce impact loads. Next slide, please. Finally, I've listed a couple of ideas for further research. It would be good to validate this hybrid approach used here, but to be able to do this, there is a need to minimize the other noise sources in the field test, such as the rolling noise. A non-linear wheel rail contact model was used in these simulations. However, we know that rail paths and ballast subgrade properties, for example, they are also strongly non-linear for the range of wheel rail contact loads considered here. So to account for this, we would also need to carry out the noise simulation in the time domain using a non-linear track model that is valid up to 5,000 Hertz. As discussed, there is a need for an assessment criterion that accounts for the specific characteristics of impact noise and relates these to other noise sources. In order to assess the disturbance due to the impact noise, such a criterion may need to account for the time history of the sound pressure, evaluate the peak levels, and combine these with a number of impacts. These results are currently not predicted with a hybrid approach, which is based on average quantities during the pass-by. And next slide, please. If you're interested in learning more about the prediction of impact loads and impact noise, I can suggest these references, where the first reference is an extensive state-of-the-art paper that collects much of the work in this area. And the second reference describes the work presented today. So thank you for your attention.
Thank you very much, Jens, for this paper, which is very much, I think, in the spirit of combining legacy or historical, if I may say, not to be provocative, frequency domain and time domain approach in the hybrid method. I think it is an emergent subject, and really we have to address now. And considering that we have dealt more or less separately the two questions in terms of rolling noise so far, I think it was very interesting to present this approach. So thanks again. There will be some questions also, but they will be kept for the end because we are a little bit late now. And I will just introduce the next